In this work, we study graph convolutions-based approach for active learning in the name entity recognition. Name entity recognition is the task for identifying different named entities in a given any unstructured data. The typical entities look like location, person's name, dates, time, or organizations. Consider this scenario. Here, in this example, Apple is the organization name, Tim Cook is the person's name, Cupertino is the location, and Flint Center is again the organization. Another example, in this case, Vancouver is the location, British Columbia again is the location, and Gregor Robertson is the person's name. Active learning. Active learning is the task of using very limited number of data to train upon and ask an oracle for the labels of few unknown unlabeled examples. In this case, we want to develop a strategy to cleverly ask our oracle to give labels for few samples that could help in improving our training algorithm. In our approach, we use two methods, uncertainty-based sampling and random sampling. For the uncertainty-based sampling, we ask our oracle to give us labels for the most uncertain examples that our training algorithm is. And we also do a random sampling in which we randomly choose few of the samples and ask labels for those samples. Unlike traditional approaches, we use graph convolutional network on the top of deep learned features. As the name suggests, graph convolutional network works on graph of arbitrarily shaped data. Traditional CNNs take rectangular kernels to give us an output. In the graph convolutional, the kernel depends on the graph structure data. There exist many different variants of graph convolution networks. In this work, we use only a fixed graph convolutional approach. We use Setoli et al.'s graph convolutional networks for named entity recognition as the base model for our approach. The non-graph convolutional network is shown in the left. On the right, on the deep learned features, we add a forward and a backward graph convolutional layers and followed by a dense layer and then a CRF output. We have also made a small change in the proposed architecture. We add a non-linear projection for the node interactions. Our experiments are set up onto nodes data set, of which we use 20% of the data for training. After we train our network, we ask the oracle to give us labels of 5% more data based on either uncertainty sampling or random sampling based approach. Base experiment. Our base model experiment is to test whether our projection to nonlinear domain has an improvement over Setoli et al.'s model. Once we prove our non-projection layer has an improvement, we then set up active learning experiments. For the active learning experiment, we do mainly three main experiments. First, once we learn the actively learned sample, we add them back to the training data and fine-tune the network. The second is we use again this actively learned samples and train the entire network afresh or from the scratch. The last experiment is based on training only on the actively learned sample from a moderately well-trained model which gave us this learned samples. In this slide, we show results comparing our change in the GCN model. The solid lines represents our results, our change results. Dashed line represents Setoli et al.'s model. The blue is for the precision curve, the green is for the recall curve, and the orange is for the F1 score. We can clearly see that for most part of the epochs using the train weights on the test set, solid lines quite outperform the dashed lines. From here on, we use our changed model as the base model for all the following active learning experiments. The first active learning experiment, that is fine-tuning with the 5% extra actively learned samples. Here again the blue is for the precision, green is for the recall, yellow or the orange is for the F1. Solid is again our model based on uncertainty. Dashed is our model based on random sampling, and the dotted represents our base model without any active learned samples. We can see that the uncertainty based approach outperforms the random sampling and the base model. The second experiment was retraining them from scratch. When retraining, the uncertainty based samples initially has hard time in getting the ideal performance, but after train for certain number of epochs, we can see that uncertainty again outperforms random and the base model. Our final experiment was to train only on actively learned sample data. For this, we trained a base model which did moderately well and had an F1 score of about 0.71 as shown here with the double line. Now we used only actively learned samples and fine-tuned with this base model. We see that after a while the model unlearns everything, and uncertainty based approach do not do well here because uncertainty samples are the hard data, and random based approach quietly overperforms the uncertainty based samples. So therefore we must use actively learned samples and fine-tune them, which was the best performing model in all the three set of different experiments that we tried. We believe graph neural networks are promising approach for active learning based on uncertainty sampling. We would like to thank all the CS410 core staff, Professor Zhai and Ismini for all our help and guidance for the successful of this project. Thank you all.